So moving forward, we're going to move into our reactions. So we've got 5 different reactions. We're just going to move straight into them. So we'll start off. This is the most basic and common one. This is a substitution reaction. This essentially involves taking one thing out and putting something in. It's like soccer or a lot of football. It just depends sort of how you refer to it. I always tend to refer to it as soccer just because AFL football, but I know it's really football. It's more of a football than our football. But we're going to say soccer just for the sake of it, to simplify things up. In soccer, you have, well, it used to be 3, it's now 5 substitutions. Those 5 substitutions essentially are that you can take a player off and put a player on. That is the same thing as a substitution reaction in chemistry. You can take a hydrogen or a chlorine or an alcohol off, whatever the off molecule is. You can take it off and you can put something on. You can put a hydrogen, you can put an alcohol, you can put a halogen, you can put whatever you want there. But you've taken something off, you put something on. That is a substitution reaction. So as you can see there, that goes on, something comes off. Oh, that was really bad, I got rid of it. The green comes on, the brown comes off. Green on, brown off. So, as you can see here, this is a great way of simplifying it. You look at those memes. So, a really good other way of looking at it is looking at how it works in terms of organic chem. So, for chlorine, this should also have heat. So, for chlorine, which is the most common example, and it's why we are going to use chlorine as our example here. If you have chlorine gas and you have a, let's just say ethane or an alkane, if you put that in the presence of heat, so you heat it up, and you put it in the presence of UV light, what happens is the hydrogen will come off and the chlorine will go on. And you end up with obviously a byproduct of HCl, but as you can see here, you've formed a haloalkane. Now, importantly, you cannot control, there are ways that are way too technical and you don't need to worry about it. For the sake of chemistry, 3-4, you cannot control where that chlorine goes. That chlorine will go anywhere it feels. So, really important. UV or heat is required, essentially it's required to break the halogen molecule. So that's what's really important. It acts as a catalyst. You must write UV heat. And I don't think it's or, I say and. It's really interesting. Some teachers and some, because I've been tutoring for a long time, so I've seen how different teachers teach students because then they come to me with questions. Some teachers have said or, some teachers say and. I was taught to always put both. So I put both. I would feel more comfortable, and I tell my students all the time, put both on your arrow. If your teacher's told you to do one, you're welcome to do it, but I feel more safe doing both because it also shows that you know both as well. So I think putting both is important. So moving through. Substitution of haloalkanes. So haloalkanes can also I think it's going to go under substitution reactions. Haloalkanes are much more reactive than alkanes. So I think it's going to say can also undergo. I do apologize. I think that was my poor typing. When alkanes, because the polar bond undergoes a bunch of different types of substitutions. One such example is the formation of an alcohol by substituting in a hydroxyl group, which can undergo further substitution to form an amine. So as you can see here, what happens is you've got your chlorine comes off, and your alcohol goes on. Now this, as we said, haloalkanes are far more reactive. You don't need anything on this arrow because it's far more reactive. It happens in a far more reactive way. There are things you can put on that arrow, but as I'm saying, it's far more reactive. It's more likely to happen. You don't need to have the heat and the UV to force it. As you can see here, when you want to add in, so it's meant to be this one down here, sorry, I don't know why, or this one down here. If you want to add in an NH3, it is a little bit different. You do need some catalysts, and as you can see there, it's Al2O3 and 400 degrees Celsius. Now, addition reactions, these are, again, a little bit different. Now, these, you are either a substitution or an addition. You're not both. Really, really important. They are the two that are distinctly different. Addition is when you don't take something out. You just break a bond and put something in. So it's when you're sort of saturating a molecule that's unsaturated. So as you can see here, we have an unsaturated molecule. We add the bromine or the bromide gas, and it goes in, or the bromide liquid, depends on what form it's in, and it goes in and forms, well, it'll be 1,2 dibromoethane. Now, what's really important here is you can't put 2 bromos on one. You can't say, oh, there's a Bi here and a Bi here, because when that bond breaks, there is a spot here and a spot here. So the bromo has to go here and the bromo has to go here. Really, really important. Comparing alkanes, alkenes are fairly, compared to alkenes are fairly reactive. So unlike substitution reactions, there's no inorganic product formed as well. So there's no, byproduct formed. There's three main types. These very rarely come up, but it's just kind of good to know. There's hydrogenation or hydrogenation. This is where we just add hydrogens in. So essentially just saying we're adding hydrogens in, we're saturating with hydrogens. There's halogenation. It's where we saturate with halogens. You can also saturate with like a HCl and put both a hydrogen and a Cl. It's still halogenation because you've made a halogen. Then there's hydration, which makes sense. You add water. Now, these are really important catalysts to remember. H3PO4 and 300 degrees. This is hydration because you're adding water and you end up with an alcohol group. So one hydrogen goes by itself, the other one ends as an alcohol group. Now, beyond that, that's about it. I would also like to talk about this just very briefly. This is what we call a bromide test. This comes up pretty frequently. This as a liquid is brown. This as a liquid is clear. This as a liquid is also clear. So, if you have an unknown hydrocarbon, you don't know what it is. You have no idea, you've just got a solution. And you've got a solution of bromide liquid or bromine liquid. You've got a brown solution. What you do is you add this in. Now, when you add it in, it's still going to be brown. Like, sure, you're adding a clear into it, but it's still going to be brown because you've got bromines in there. So it's going to be brown. When you add this in, if it all goes clear, if it adds in, dilutes, and then all of a sudden it goes clear, like after a couple of seconds it goes clear, everything disappears, what that tells you is that all of this has been used up into this. So it tells you that you had an unsaturated molecule. You had an alkene or an alkyne. Now, if the solution stays brown, it means you already had a saturated molecule. Your hydrocarbon you added in was already saturated. So, therefore, your bromine or your bromide, your liquid was unable to react. It wasn't able to disappear, so you still got that molecule in there. It's still brown. Therefore, you had a saturated molecule already. That's a bromide test. So that does come up. Important to know. Now, pushing through because we are running out of time for this side of the topic because we are, I think we're already like an hour and 8 minutes in, which is pretty good. So I think if we get this done in an hour and 15, we can move into the second part and spend about 40, 45 minutes on it, which is pretty good. Oxidation reactions of alcohols. So alcohols essentially can go through primary and secondary alcohols or alkanols, same thing, can be oxidized by really strong oxidants. So as you can see here, you need to remember one of these. So H plus with Cr2, so it's dichromate, Cr2O72 negative, or a word I can never say right, penanganate, I can never say it right, but it's H plus with MnO4 negative. Now, these are really, really nasty molecules. They're really strong oxidants. You add them in with alcohol and you're going to get either a ketone or a carboxylic acid. There will be aldehydes in there, but there won't be many. I'll explain why in a second. You essentially get this pathway here. You get primary alcohols going through a two-step pathway. You get an aldehyde in the middle. However, these aldehydes are highly reactive, and 99% of them will go into this. 99% of them are going to continue on the pathway and go to carboxylic acid. That is why I said you're pretty much just going to have carboxylic acids and ketones. You're not going to have any aldehydes because aldehydes are so reactive they just move forward. Ketones form from secondary. So if you have, this is what you form, this can no longer form a carboxylic acid because you can't add an OH group here. You've already got 4 bonds. This isn't possible. So that's why secondary alkanols cannot form carboxylic acids. They're not as useful. They just form ketones. And ketones are really not that useful. Tertiary cannot even form a double bonded oxygen because tertiary, if you think about it, and there's a carbon here, and then you've got your OH. If you want to form a double bond there, you end up with 5 bonds. So again, not useful. So that is why primary alcohols are the most useful and are the ones that we're going to utilize the most. And as we said, Secondary alkanols form ketones, really not that useful. Now, tertiary alcohols don't undergo oxidation. Cool. Now, this is oxidation. You've already been through redox, so should be pretty sort of straightforward to understand. Now, this is what the pathway looks like. As you can see, you've got the same catalyst for both. The same catalyst for both is really, really important. Please don't write dichromate on one and then penanganate on the other. You need to stick with one of them. And it doesn't matter which one you use, just pick one and stick with it. And that's sort of how you go about it. And then here's secondary. As you can see, it's just one step. You can't go any further. Also sort of kind of relevant because you may use it in sort of an experiment. Dichromate is generally orange, whereas penanganate is like a purpley navy color. So it's kind of useful to see. You can kind of utilize those and utilize that information in questions. It's quite useful. So do sort of try and remember that. And that's sort of about it. So it's kind of useful to know that. I'd say that's probably about it from that side of things. And then we have esterification. So esterification is where we form our ill OH, and we've already talked about this very briefly. But as you can see here, you have a carboxylic acid with a primary alcohol. Really important, you have to put it with a primary alcohol, and it yields an ester. So this is a condensation reaction, which releases H2O. You need to heat the reaction mixture with the presence of concentrated H2SO4. Now, really important, you either write concentrated or conc with a full stop, I mean concentrated, H2SO4, or you put H2SO4 liquid. Both of these are acceptable, but nonetheless, you just need to do one or the other. So we've got, as you can see here, you've got ethanol and you've got propanoic acid. You put them together with H2SO4 and you end up with this molecule here. Now, what's really important, and this is what we didn't discuss earlier, is what is lost. This is lost and this is lost. When these come out, what do you think they form? You've got two H's and an oxygen. What does that sound like? It sounds like H2O. So you have H2O as a side product. For those of you who do biology, you will have heard of this as a condensation reaction. And that is what this is. This is also a condensation reaction. You can call it either condensation or esterification reaction. Either of them work. I don't mind. I'm happy for you to go with either of those. So they're the two things that you need to know. So here's a really good question. So what is the systematic name of the product of this that this reaction forms? Again, those of you at home, feel free to pause and take your time. Those of you here, I'm only going to give you like 20 seconds. So you're going to get 20 seconds from here. So go for it now. All right. So from here, what have we got? We've got a chain that can start either here or here. Doesn't really matter. You got 1, 2, 3, 4, and then an alcohol. So I'm going to call this, this is going to be bute and 1-ol, but it's also going to have on the other end, so I probably shouldn't use a capital there. I should use a lowercase. On this end, it's going to have a methyl group, and that's going to be at the 1, 2, 3. So it's going to be 3 methyl butanol. It shouldn't have a space, but the way I've written it, sorry. All right, then from here, we are going to go, all right, if I put this in and I go forward, what am I going to end up with? Well, I'm going to end up with an oic acid. You may end up with an aldehyde, but as you can see here, it's only giving you oic acids. So we end up with an oic acid. This is still going to be butanoic acid, so it can't be A or B. It needs to be butanoic acid, and this is going to be at the first spot. So this is going to be an O, this is going to be an OH, that's going to be 1, this will be 1, 2, 3 again. So it's going to be this one here, 3 methyl butanoic acid.